Hello and welcome. In this explainer, we are going to break down one of Java's most powerful and, let's be honest, most frequently used tools, the HashMap.
Have you ever really stopped to think about it? How does a Java HashMap pull one specific value out of potentially millions of entries in what feels like an instant? I mean, it seems like some kind of magic, but it's really just some seriously clever engineering.
And the magic behind that incredible speed, it's all thanks to a concept called hashing. This is what makes the data access so ridiculously fast. Okay, let's get into it.
By the end of this, you'll know exactly how HashMap uses this hashing technique to store and retrieve your data so efficiently. No more mystery. Here's our game plan. We'll start with the basics. What even is a HashMap? Then we'll uncover the secret of how hashing really works. After that, we'll look at how you work with it day to day. And finally, we'll cover the critical rules you've got to know for top performance. So first things first, let's just make sure we're on the same page about what a HashMap is. It's seriously one of the most fundamental data structures you will ever use in Java.
The best way to think of it, it's a super efficient dictionary. You use a unique key, like a word, to instantly look up its value, which is the definition. In the computer science world, we call this constant time or O1 performance. All that really means is the lookup speed doesn't change whether you have 10 entries or 10 million. It's just fast. And in your code, it's super simple. You just create a HashMap object, and then use the put method to add your key value pairs. So here, we're using a student's name, which is a string, as the key, and their score, an integer, as the value.
So how in the world does the HashMap find these values so quickly? It's definitely not just scanning through a list from top to bottom. No, the real secret is in how it stores the data in the first place.
Okay, when you put something into the map, a three-step process happens behind the scenes. First, it takes your key and calls a method called hashCode to get a number. Then, it uses that number to figure out an index, a specific spot in an array it keeps internally. And finally, it stores your key value pair right in that spot, which we call a bucket.
Right, that's a great question, because this is bound to happen sooner or later. What if two totally different keys end up calculating the exact same storage spot?
Well, that's called a hash collision, and HashMap has a really elegant way to handle it. Instead of just overwriting the old data, it's designed to store multiple entries in that one single bucket.
And this right here is a brilliant evolution in Java. See, before Java 8, a bucket with collisions was just a simple list. If you got really unlucky and had a ton of collisions, searching that list could actually get slow. But now, if a bucket gets too crowded, it automatically transforms itself into a highly efficient tree structure. This keeps your lookups incredibly fast even when there are a lot of collisions. It's a game changer.
Okay, so now that we know what's happening under the hood, let's look at how we actually work with these keys and values in our day-to-day code.
Getting a value out is as simple as calling get with the key. And notice this, if you put a key that's already in there, like John, it doesn't throw an error or anything, it just updates the value. Easy as that.
And you've got a whole toolkit beyond just getting and putting. You can remove entries or just check if a key exists without actually fetching its value. You can get the total size, and really importantly, you can loop through all the entries very efficiently using entry set.
Here's an important little detail. HashMap is a bit more lenient than some of its cousins. It'll let you store one null key and as many null values as you want. Older collections like HashTable or sorted ones like TreeMap, yeah, they'd throw a fit if you tried that.
All right, let's get to the crucial stuff, understanding the performance you can expect and the rules you absolutely must follow to make sure your HashMap works correctly and stays fast.
This table really shows the magic. On average, these operations are constant time, or O of 1. That just means they're incredibly fast, and their speed doesn't depend on the size of the map. Even in the worst-case scenario with tons of collisions, the performance only dips to O log n, which is still extremely efficient for massive data sets. And that's all thanks to that automatic tree conversion trick we talked about.
Okay, listen up, because this is the single most important rule to remember. If you use your own custom objects as keys, you must provide consistent hashCode and equals methods. The rule is simple. If two of your objects are equal to each other, they must return the same hashCode. If you get this wrong, your map will break in very confusing ways. You'll put an object in, but when you go to retrieve it, the map won't be able to find it. It's like your data just disappears into the void.
And one last critical note on safety.
Your standard HashMap is not built to be used by multiple threads at the same time. If you're building a concurrent application, you'll want to use concurrent HashMap instead. It's designed for that and will save you from a world of headaches and data corruption.
All right, to help all this sink in, here's a little challenge for you. Just pause for a second and try this out. Write the code to create a HashMap, add a few key value pairs, and then update one of them. It's a great way to make sure the syntax sticks.
So, to wrap it all up, HashMap perfectly blends a simple, easy-to-use interface with a really complex and highly optimized engine under the hood. That balance is what makes it such an essential go-to tool for pretty much every Java developer out there. And that leaves us with a final thought to chew on. We know HashMap is all about speed, right? But when would you ever choose to trade that speed for a map that actually keeps its keys sorted, like a TreeMap? In what situations does the order of your data become just as important as the data itself?